Hey class, it's Mr. Hofstad here with lesson 5. This lesson has no notes, pretty exciting, only an example, and it's going to be combining circular motion, unit 5, what we've been doing, with unit 4, energetics, what we were doing last unit. So we've looked at pendulums in terms of the energetics, right? But now we're going to kind of switch our way of looking at it and think about it more in a uniform circular motion way, right? Because if, right, this pendulum were to continue, it's kind of undergoing circular motion, not necessarily uniform because the speed is changing, but we can take kind of a snapshot of it at a certain point in time and apply our framework of circular motion thinking to this example. So here we go. I've got it drawn out on my whiteboard already. We've got our pendulum, right, a length of 3.4 meters. Attached to it is a giant 400 kilogram, I'm going to call it a wrecking ball because that's massive. And it's starting at 1.6 meters above its reference height, right? That equilibrium point there. So in order to determine the maximum tension, we have to know first of all where maximum tension occurs. So two lessons ago, we looked at maximum and minimum tension in vertical circles. This wrecking ball is essentially a vertical circular motion, and we can go back in our notes or quickly recall that the maximum tension occurs at the bottom of the circle, right? And if we look at the free body diagram of that, we can verify that quickly. So here's our wrecking ball with the rope attached to it. So our free body diagram would have force of tension up, force of gravity down, and it'll be accelerating towards the center with centripetal acceleration upwards. So if we were to write our net force equation out, we'll say force of tension is positive because it's up, right? Our reference maybe is up is positive. Either would work, but this is more standard to use positive as up in this case. We're going to subtract force of gravity, and that'll be equal to our mass times our centripetal acceleration. So if we solve for Ft, right, it becomes mass centripetal acceleration, and we're adding force of gravity to it. So since we're adding force of gravity, that's a bigger number. That's our maximum tension, and it's going to be occurring at the bottom of this here. So our end goal is to find this value here. We already know force of gravity from mass and gravity. In order to actually solve for this tension, though, we're going to need our centripetal acceleration. So that's going to be our first step. The question doesn't tell us anything about speed, doesn't tell us anything about period. But if we think about energetics, we can actually calculate the speed at the bottom. Find the maximum speed. So our maximum speed is going to be at the bottom. We know that both from energetics, right, and even in essence from our circular motion unit here, right? It's going fastest at the bottom of that swing. That's part of our simple harmonic motion as well. All right, so we're going to use energy to solve for this. The total mechanical energy at the start is equal to the total mechanical energy at the end. So at the start, that's going to be all gravitational potential. At the end, we're going to call this the end. That's going to be all kinetic energy. So gravitational potential is mass gravity times height. Kinetic is half mass speed squared. We're trying to find its speed in essence so we can find the centripetal acceleration, speed squared divided by radius. So we're going to rearrange our formula to solve for speed. We'll divide both sides by mass. We'll see that they cancel. And we're multiplying by 2 here. So speed is equal to the square root. Don't forget about our square. pesky square is always showing up, times 2 gravity height, which is, I'll keep that below actually. Speed is equal to the square root of 2, 9.81, and a height of 1.6 meters at the start, right? That's our height initial, 2.6 meters. And that gives us 5.603 meters per second. That's our max speed, V max, and that's happening at the bottom. So we're going to use this speed to find our centripetal acceleration, right? Because we're now trying to find the max tension, which is also at the bottom. So we're going to restate this force of tension here. Force of tension is equal to mass times centripetal acceleration plus the force of gravity. All right, or that would be mg. So solving for centripetal acceleration, I may as well do it here because I'm running out of room. Centripetal acceleration is equal to 5.603 squared divided by the radius, which was 3.4 meters. That gives us a centripetal acceleration so our mass is 400. Centripetal acceleration comes out, well, let's just keep it all together, right? We'll replace AC with V squared over R. 5.603 squared divided by 3.4. And we're going to add that to our mass and gravity, 400 times 9.81. So 400 times centripetal acceleration plus 400 times gravity gives us 7.62 times 10 to the 3 newtons or kilonewtons. That's all we got for energetics, I believe. Let me double check. Yeah. So you're going to have to maybe go back in your notes to some of the energetic stuff to solve this, right? We're going to be working with a lot of conservation of energy, right? And then throwing in all of our circular motion, centripetal acceleration, centripetal force, whatever it might be. This is going to be a lot of creative thinking and problem solving on your part. So good luck. Let me know if you have any questions. Talk to you later.